Hey, Carly.
Hey, Wade.
Now let's use Python to program a linear regression model using the sklearn library. So to build a linear regression model, we're always going to use 3 steps. The first step is going to involve initializing the machine learning model. And we're always going to need to initialize the model whenever we're using a linear regression. This is just like loading a data set in a data frame. So just like we have a read CSV or a pd.data frame, we need to create an instance of the linear regression model inside of Python. So to do that, we need to do 2 steps. We need to import the right library from the sklearn library. And the second step is we need to actually make a new model, a variable called model. So the first step is we're going to use linear regression. And the linear regression model in sklearn comes from the linear model library inside of sklearn. So to import this library, we'll do from sklearn.linear_model, all lowercase. Then we're going to import linear regression with a capital L and a capital R. And this is going to give us the linear regression model inside of Python. Then we need to create a new instance of that model. I'm just going to call it model. You can call it whatever you want, but I'm just generally going to call it just model, just like I call all my discrete variables D. I call all of my data frames df. So I'm going to say model is equal to linear regression, capital L, regression, capital R. And then I'm going to open and close my parentheses. And that is going to create a new linear regression model. So there is going to right now be nothing in this model. So it hasn't learned anything. So now we got to decide what do we want this model to learn. So all machine learning models require training. sklearn fits the model with the training data. So we must give it a list of input columns. We call this the input independent variables and the known output for each input. So we know that linear regression is a supervised machine learning algorithm, so we need to give it the correct answer. So let's think about the size of the diamond data set. So the most obvious prediction of the price would be the size of the diamond. So if we want to predict the price from the size, that means the size comes first. So the sizes are x. And
so I need to import the diamond data set first,
yes,
right?
Yes, we're going to be importing diamond data set. So while I'm working on that, you can go ahead and grab that.
Perfect.
Which is on my faculty website, waf.cs.illinois.edu/discoveries/diamonds.csv. And we're going to predict the price from the size of the diamond. So the size is going to be our x variable, or our independent. And then the y is going to be our dependent variable. It's going to depend on the size. So given a size of a diamond, we're going to predict its price. So we need to go ahead and create a list of all of our independent variables. So to do that, I'm going to go ahead and create a list right here and say, I need to know the column name for the size of the diamond. So Carly, if you just do df, you should be able to see the column names. What's the column name for the size of the diamond?
It looks like it is caret.
Caret. So size of the diamond is often just referred to as the caret weight, because that's going to be the best metric for the size of the diamond. So I'm going to say it's caret. And then the dependent variable column name is going to be the price of the diamond. And what is the price of the diamond?
It just says price.
Awesome. Price, all lowercase. So now I know the list of all my independent variables and my dependent variable. So I'm going to go ahead and fit the model that we just created. So I'm going to run model.fit. And I'm going to say inside my data frame, I'm going to ask for the columns of all my independent variables. So df at, and then inside of that, I'm going to give a list. So I'm going to have 2 open brackets all at once. Caret. So I'm placing this entire list right here that I identified earlier in here inside my df. And then I'm going to comma. So my independent variables is df at the list that contains caret. And my dependent variables is df at price. And when you run this, you should get either no output or just 1 line of output.
1 line of output, but it's not an error.
Yeah, and it says just that the model has been trained, essentially.
Yes, linear regression, and then a bunch of other stuff.
Awesome. So the third step is always going to be to predict the diamond weight, or to predict any information based on our model that we trained. So here we've trained our model to take in carat weights and predict prices. So we know in our model, our independent variable is simply just carat. So if we want to predict the price of a 1 carat diamond, I'm going to use the same format in model.predict. And I'm going to open inside the parentheses, I'm going to open a square bracket to give a list of all of the predictions we want to make. And inside this inner list, I'm going to say, I just want to predict 1 diamond that has a carat weight of 1 carat. So model.predict, open parentheses, double square brackets, 1, close double square brackets.
Got it. And I got array 5500.07.
5500. So the machine learning model read in our entire data set. And from this data set, we asked it to, using all 54,000 plus diamonds, predict the price of a 1 carat diamond. And it predicted that price was $55,000 or $5,500.
Yeah.
So let's do this exact same thing. What's the prediction of a 2 carat diamond? So I'm going to do it 2 different ways. The first way, I'm going to just do model.predict, just like I did before, open parentheses, open up a double list, put a 2 now instead of a 1, close the list. And Carly, what is our prediction for a 2 carat diamond?
$13,256.49.
$13,256. So $13,000 plus for a 2 carat diamond. So it was able to predict 1 carat, 2 carats, and just kind of show off that you can do multiple predictions all at once. I'm going to do this here as well. And I'm going to do model.predict. And I'm going to open my parentheses. Then I'm going to start my list. And this list is now going to contain a list of all the predictions I want. And so the first element in my list is going to be a list that contains only the number 1, and then a list that contains only the number 2 separated by a comma. So basically, I'm giving 2 different sets of our independent variables. And the first set is only the independent variable 1. The second set is only the independent variable 2, since it's only simple linear regression. So Carly, if you run this, what do you get?
I get 5,500, comma 13,256.
So now you see the result is 2 different predictions for the 2 different inputs we give.
Yes.
So what is the prediction of a 20 carat diamond? So Carly told me not to do this.
Yeah.
But I definitely want to know what the computer is going to give me. So I'm going to go ahead and do model.predict of square bracket 20, close, close. And what do we get?
$152,872.
$152,000.
Yeah.
So is this answer reasonable? What is the real cost of a 20 carat diamond?
I don't know.
So I was looking at a news article just the other day. So a celebrity bought his wife a 20 carat diamond, and it cost them tens of millions of dollars. The actual price wasn't known. It's expected to be between $15 and $25 million.
Oh my gosh.
So is $152,000 a reasonable price?
No, it seems like it increases exponentially.
Nope. What's the real price? I'm going to say $10 million plus. I'm not sure what the real price is. There's very few 20 carat diamonds out there, but it's probably going to cost you at least $10 million. Definitely not just $150,000.
Yeah.
So what's the reason for this, Carly? I think you had a rationale for this.
Yeah, so this is the idea of extrapolation. We're assuming that there's this linear relationship that continues outside of our range of data. And clearly there's not if this diamond really costs $10 million plus. So we don't want to extrapolate because we're making an assumption that may or may not be true.
Yeah, so 20 carat is outside of the range of our data set. So this is a form of extrapolation.
Yes, which we want to avoid.
Extrapolation is bad.
Dangerous.
Yes. So awesome. We can now use this prediction to have Python predict all of the predicted values for all of the diamonds in this data set, which will help us find the residual and the error in this data set.
Yeah, that sounds good. So we can get basically a column of predictions for every single X value.
Exactly. So let's go ahead and first just see this happen. So let's do model.predict, and instead of predicting a particular elements, instead of just like predicting 1 carat diamond, let's inside our model.predict, let's have df at And then we're going to include the entire list of all of our independent variables. So df at, and then our list is going to be just the variable caret. So df double square brackets caret. And if I just run this model.predict, I should see the output should just be one long list that contains lots of values.
Yes, and it has a dot, 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 so I can't see all of them, but.
So what this is every single row has a predicted value, but I want to save this as part of our data frame. So I'm going to just go ahead and say df at price underscore predict to give us our price, but the predicted value is equal to that line that we just wrote. And that's going to add the predicted price column to our entire data set.
And I went ahead and did that, and then I looked at df, and I have a variable at the end of the data set called price underscore predict.
Awesome. So now we have both the price and the predicted price. And now we want to calculate the residual, or the prediction error. So Carly, when you calculate a residual, how do you do it?
So I always think it's the actual value minus the predicted value. So it's that difference between what we predicted and then what the actual value actually is.
So the error is the actual minus the prediction?
Yes.
So let's go ahead and do that exact thing. So I'm going to create a new column, df at error is equal to df of the actual value is the price minus df of price underscore predict. We added a new column called error. So if we look at the data frame again, we should have a new column.
Called error, yep, we're at the very end. And there's some negative values and some positive.
Awesome. So we know a linear regression should have the minimum error possible. So that means there should be some error above and some error below.
Yes.
And so is this prediction going to be too high, too low, or both? And looking just at the error column, we see some are too high and some are too low, right?
Yeah.
So the predictions are both too high and too low. So what I'm actually wondering is, what is the total prediction error? Let's just sum up all of that. So let's do df at error dot sum. And let's find the total error. If I add up all the positives, all the negatives, all the total errors, and all of these different diamonds, what's the total error, Carly?
So I actually get negative 5.49 times 10 to the negative 8.
Times 10 to the negative 8. So
essentially 0.
Yeah, negative 5.49. That means I can, to the negative 8, I move the decimal point 8 positions to the left. So that's going to result in 7 zeros, 549. So 7 zeros, 549. And basically, there's a tiny amount of rounding error that Python made because we did multiple independent steps.
Right.
So we introduced a tiny amount of error. This error was tiny. It's less than 1 in 1/1,000,000th. So times 10 to the negative 8th. So we see that this number is 0. And in fact, if we had perfect accuracy through the entire process, the sum of all errors in all linear regression is always going to be 0. That the exact amount of positive error cancels out with the exact amount of negative error. So this is a really neat feature, that we always have this exact value of error. So that is why if we want to calculate how much error there is across the entire model, we need to create a different metric. So Carly talked about other metrics that we can look at, like you often look at the root mean squared error.
Yep, because we can't, it might make sense to say, well, should we just look at the average amount of error, but that's always going to be 0. So instead, if we look at the standard deviation of the errors, also known as the root mean squared error, we can actually have that be a number that's not 0.
And other people, including a lot of data scientists, will often look at the mean average error, or the mean absolute error, the MAE, which is just simply taking the absolute value of things and then finding the average error across all the values with using only positive numbers. So this results in a similar metric as the RMSE, except for you take the square and then the square root. And because you're squaring the numbers, the RMSE is actually going to be more volatile to high outliers. So depending on how much you want the outliers to affect the quality metric or the error metric of your data, you might use the RMSE or you might use the mean absolute error. These are both ways that we can compare the model without having this problem that the actual error itself, if you add and subtract all the errors, is always going to be 0. Hopefully this gives you some insight into some linear regression models, and now you know how to build your own linear regression model using the sklearn library.